Okay, hello everybody. This is just going to be a quick video to let you know what you should know for exam 3. And the first thing that you need to know for exam 3 before I even get into any of this stuff is everything from exam 1 and 2. Okay, those are going to be kind of prerequisite knowledge. Most of the exams should test your knowledge of material from what's happened in between exam 2 and this exam. However, as you know, math tends to stack, so there will be some concepts which you will need to know from these previous exams in order to do problems from this exam. But the purpose of this video is really just to tell you everything new that we've learned and that you should really focus on studying for the third exam. So jumping right in, we'll start off with 5.1. What we need to know from 5.1 is the relationship between distance, velocity, and acceleration functions, okay? So in particular, velocity is the derivative of the distance function, and maybe I should write this out. D prime of t is going to be equal to v of t, and the derivative of the velocity function is the rate of change of the velocity, which is the acceleration. So those are things that you should know, and you should know how to look at the graph of the velocity function and say something about the distance function. Okay, if we look at the graph of the velocity function, then the distance traveled is going to represent the area underneath that curve. And same thing for acceleration. If we look at the acceleration graph, then the velocity will manifest as the accumulation of area underneath the acceleration curve. So you should know that relationship between those three things. You should also know how to compute Riemann sums, okay? So left and right Riemann sums for finding the area underneath a curve. Don't forget, when we're doing left and right Riemann sums, the letter n we use to represent the number of rectangles for our Riemann sum. And the way we get the width of each rectangle is we take delta x, that's the width of each rectangle, we set that to be equal to the length of our interval, b minus a, and we divide that by the number of rectangles that we want. So we just divide the total length of the area into n equal portions. So that's 5.1. 5.2 then goes on to kind of explain what the definite integral of f of x over the interval from a to b means. So we write this with the notation integral from a to b of f of x dx. That means we're doing a definite integral, and we define it to be the area underneath f of x from a to b. Okay, and one important fact that we learned in this section is that if we take a is less than b is less than c, then the integral from a to c of f of x dx is going to be equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So, for example, on this graph, well, let me make this graph go from a to c here, and we'll put b somewhere in the middle. Then the area from a to c is just going to be the area from a to b, and then we add to that the area from b to c. And if we add those two areas, then we will get the orange one. So that's a fact that you should know. And what we really said was that the real quote-unquote definition of the definite integral from a to b of f of x dx is actually going to be the limit of the right or left Riemann sums as n goes to infinity. So if we just take a look at this graph here and we approximate the area using rectangles, and we just do a better and better job by using more and more rectangles, then eventually we will have a really good estimate of our area under the curve. If we just continue using more and more rectangles and more rectangles, then our estimate will get better and better and better. And if we look at the limit of this process, so the number that it seems like it's going to when we keep doing these Riemann sums with greater and greater numbers of rectangles, the limit of that process will be the true area under the curve. So that's what we need to know from 5.2. Oh, we also should know that if f of x is a negative function, okay, so if it's lying beneath the x-axis, then the integral from a to b of f of x dx is going to be the negation of the area underneath the x-axis. So we take this area which is trapped between the function and the x-axis. If it happens to be beneath the x-axis, then the integral of this function will be that area but negative. So another thing that I'd like to point out here is that if we have a function which is sometimes positive and sometimes negative, say we have some function which looks like this, then if this is a and this is b and this is c, then the integral from a to c of f of x dx is going to be equal to the area which we have trapped above the x-axis, and we're going to subtract from that the area which we have trapped beneath the x-axis. Okay, so that's how we're going to find that. So if we had, for example, a problem which asked us to find the total area between f and the x-axis, that would be equal to the integral from a to b of f of x dx, that's the green area, as a positive number, and then we would subtract the negative number integral from b to c of f of x dx. Okay, the reason I'm subtracting here is because I want to actually add these two areas, not subtract. Okay, so I want to point out that these two things are different. Okay, integral from a to c of f of x dx does not mean the same thing as the total area between f and the x-axis. Okay, so that's one thing there. 5.3, really the main new thing that we learned in 5.3 was just area between curves. So if we have two functions, which are, one is above the other one, and we want to find the area between them, well, we can think about taking this orange area here underneath f, and if we subtracted from that the area which is beneath G, which is this shaded region here, so if we subtracted from the orange highlighted area the red area, then we would wind up with the purple shaded area. So that's what we do when we want to find the area between curves. We just take the integral from a to b and we take the top curve minus the bottom curve. Okay, so in our case, f was on top and g was on bottom, so we did f minus g. Okay, 5.4, we talked about the units and interpretation of integrals, like in word problems. So the integral from a to b of f of x dx has the units, which are the product of the units of f of x and the units of x. So if f of x was in miles per hour and x was in hours, then we would take miles per hour times hours and we would get miles. Okay, so example, miles per hour times hours, that's miles per hour times hour over 1 equals miles. So that's how we do that process. And the really crucial thing we learned in this section was that if f of t is a rate of change in a quantity, then the integral from a to b of f of t dt will represent the total change in that quantity from t equals a to t equals b. And we had a really challenging problem in this section, which is just to say that f of t can really be the rate of change of any quantity. And the problem that we had that was challenging was when that quantity was itself a rate of change. It was the beats per minute of a heart rate of a runner. And we had some function which measured the rate of change of that rate of change. Well, the integral from a to b of any rate of change will give us the total change in the quantity which f of t is a rate of change of. So, in particular, if we have a rate of change of a rate of change, then this will give us the total change in the rate of change of that function. So that's a bit of a tongue twister, but the point is that if f is a rate of change, the integral from a to b of f of t dt will represent the total change in the quantity from t equals a to t equals b. Okay. 5.5 was fundamental theorem of calculus light. Okay, and they said that if we have some function capital F of x and its derivative capital F prime of x is continuous on a comma b, then the integral from a to b of capital F prime of x dx equals capital F of b minus capital F of a. So what this really says is that if we take the derivative of a function and we integrate it from a to b, what we get is the difference in height between the function evaluated at b and the function evaluated at a. Okay? So integral from a to b of the derivative gives us the total change from a to b of our original function. I'm going to pass over this one kind of quickly because we're going to talk more about the fundamental theorem of calculus for 6.3. So 6.2 is when we learned how to do antiderivatives. So for this section, you should definitely know how to find antiderivatives and the significance of plus c. You should know also that antiderivatives are not unique unless we are given additional information. We call those initial value problems when we have additional information. Okay, so in terms of knowing how to do antiderivatives, you should know how to do the antiderivatives of polynomial functions. You should know how to find the antiderivative of a constant. You should know how to find the antiderivative of e to the kx. And you should know how to find the antiderivative of 1 over x. So remember, integral of 1 over x dx is ln of absolute value of x plus c. So that's one thing that I'll write down. The other ones, I'll leave it to you guys to check the book or our notes. Okay, you should know what the definition of an indefinite integral. In particular, you should really know what the difference is between an indefinite integral and a definite integral. The indefinite integral of a function is the general antiderivative plus c. Indefinite integral gives us a class of functions. It's the set of all functions which are antiderivatives of the integrand. Okay? In contrast, a definite integral is going to give us a number. It's going to represent the area under the curve, or the area under the curve which is above the x-axis minus the area trapped between the curve and the x-axis, which lies beneath the x-axis, like we did before. Okay, so definite integral, we get a number. Indefinite integral, we get a class of functions. These facts here are actually true whether we have indefinite integrals or definite integrals. So if we do the integral of f plus g dx, then we're going to get the integral of f dx plus the integral of g dx. So we can split these up based on the sums. We can just do the antiderivative of each piece by itself. Likewise, if we multiply by a constant, we can bring that constant out front and just say that the integral of a constant times a function is the same as multiplying the constant times the integral of the function. And these also work if we were to put a and b here. We can put a and b here and a and b here. That's perfectly fine. We can do this with definite integration as well. But we don't necessarily have to. Works for both. Okay, so that's 6.2, mainly about finding antiderivatives. Okay, so 6.3, we talked about the fundamental theorem of calculus again, and we gave sort of what I feel like is the better way of writing it. We said that if little f of x is some continuous function, and capital F of x is any antiderivative, we can just pick whichever one we want. Okay, capital F of x is any antiderivative. We know there's lots of them because we can add any constant that we want. Okay, so we just pick any antiderivative of little f of x, then the integral from a to b of little f of x dx. So, in other words, area under the curve. This is area under f of x from a to b. It's just going to be equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Sometimes we write that as like capital F of x, and then we'll do this little line on the right-hand side with a and b, meaning that we should plug in b first and then subtract and plug in a. Okay, so we should know how to use this to compute integrals. So if I gave you something like the integral from 1 to 2 of x squared dx, you should know that we need to find the antiderivative. I'm going to use the 1 x cubed over 3. That's one antiderivative. And I'll evaluate it at 1 and 2. And so I would plug in 2 first. I'd get 8. 2 cubed is 8 divided by 3. And then I would subtract 1 cubed over 3. And so I would get 7/3. Okay, so that's one way that I would use the fundamental theorem of calculus to compute an integral. Okay, last section, we need to know how to use U substitution. And we should know how to use U substitution for indefinite integrals and for definite integrals. In particular, for definite integrals, use either method. I'm not going to ask you to use one method over the other. Just use whichever one you feel is the most comfortable for you. Okay, most comfortable for you. So let me just remind you really quickly what U sub is about. If we have integral of f prime of g of x times g prime of x dx, we're gonna choose u to be g of x and du to be g of x, g prime of x dx. And then this integral will become the integral of f prime of u du. And we know that if we integrate the derivative, we will just get the antiderivative of the derivative is the function. So this will just be f of u plus c, and then we would switch back to x, and that would just be f of g of x plus c. And we can check our work that if we were to do the derivative of this function here, we would get back our integrand, f prime of g of x times g prime of x. Okay, and really quickly, I'll just remind you that if we want to do the integral from a to b of f of g of x, f prime of g of x times g prime of x dx, then we choose u equals g of x, du equals g prime of x dx, and our new integral is going to be two methods. First method, we'll do g of a to g of b of f prime of u du. And then we'll just solve with u. Or method 2 is do the integral from what we say x equals a to x equals b of f prime of u du, and then we need to switch back to a function of x. Function of x. And then, and only then, can we plug in. Because we want to make sure that we don't plug x values in for u, okay? Because those are x values, they aren't u values. So we either need to change them into u values, that's method 1, where we plug in g of a and g of b, or we need to leave them as x values and then make sure we change back to x before we plug in. Those are the two options. Okay, so these are really the main key points of every section that you should be taking away. So if you're watching this video and you're thinking, oh crap, I don't remember some of that stuff from 5.2, you might want to go back and study that sort of thing. However, this is definitely not comprehensive, okay? I really just hit the big things. Within each of these sections, there are a lot of things that I didn't write down in this video that are important to know. This is just kind of the highlights to hopefully help you identify what you might want to be studying. So yeah, I think that's all I have to say about that. Happy studying.